I'm just going to start. Okay, approximate and L'Hopital's rule. Let's go. So the first part is infinity math right here. And here's what I mean. I want to go over, like, what does it mean to multiply by infinity and do things to infinity. So infinity, the idea is this is just a number that continues to grow. I don't even think of it's a number. It's like a concept that we just have an ever increasing number. So a little bit of math behind this. If I go infinity times 1, okay, I have to do it that way. If I go infinity times 1, that's still going to be infinity. If I did infinity times 5, still infinity, any times any constant, right? Those are all going to be infinity. If you go to infinity and you like divide it by 5, we are still infinity because it's just growing. Who cares if you divide it by 5? Same thing with multiplying. So multiply, divide doesn't change things. Now, yeah, if you did a negative, so I go infinity times -5, I would now have negative infinity. So it does still follow those rules of negatives. Now, if I go infinity plus 1, we're still infinity. It doesn't matter. Infinity minus 3. Would this be maybe negative infinity? No. Still positive infinity. So that stuff doesn't matter. If I go infinity squared, we're still infinity. All right? So all that stuff, rubber band broke, who cares? Still infinity. Now, if squared doesn't change it, what if I go the square root of infinity? Well, that's still infinity. All right, no problem. Okay, now you might be like, well, what does change? Okay, so things that could change. What if I go 5 divided by infinity? You divide by infinity, and this is going to infinity, it's effectively, since the bottom is growing forever and it's infinity big, we just say this is 0. All right? So if it's 1 over infinity, it's 0. If it was -3 over infinity, oh, does that go to negative infinity? No, it means it's 0. And the -0 is not really a thing. So I think those are some of the key concepts of infinity, that how they come out to numbers, okay? You multiply it, you divide it. The negatives will still be a thing. You take it to a power or root it, we're still infinity. If you divide it by infinity like this, we're 0. What if I did like 1 over infinity squared? That's still just like 1 over infinity. Still 0. What if I did e to the negative infinity? What is this? Oh, first of all, before I do that, what if I did like 2 to the infinity power? Well, that's just still infinity. But if I did 2 to the negative infinity power, that's equivalent to 1 over 2 to the infinity. It's like 1 over infinity, which is 0. So careful with the negative exponents, because then they just convert to the bottom. That's sometimes a way to trip you up. What if I did e to the 1 over infinity power? That's like e to the 0 power, which would just be 1. So a few little weird things that could pop up that maybe that's relevant to this lesson. We'll find out. Now, we also have things we call indeterminate forms. So, 0 divided by 1 is 0. And if I did 1 divided by 0, so 0 divided by 1, if I did 1 divided by 0, sometimes we call this undefined or does not exist. But what if I get 0 divided by 0? We call this indeterminate. And we also call that, like, infinity over infinity would also be indeterminate. Like, we don't know what that is, or you can't determine it in this form. You can't say it's undefined. It's not really undefined. Does not exist. Not 0. You don't cancel these off and say, oh, they just cancel out and it's 1. Doesn't work that way. It's in the form that created this. we cannot determine what it is. So we must either apply different rules or change it to a different form. Now, this is the most relevant when we're dealing with limits. So, especially indeterminate limits. So that's like when I say the limit of something as x goes to whatever, some value a of some function. What if that comes out to, usually it's like a fraction. It's like infinity over infinity or 0 over 0 when you plug it in. Now, I think we did it before. And it's like, oh, you had to do like some factoring stuff. But we can also do like L'Hopital's rule. And that's what we're getting at today. I think we've done this a little bit already. So nothing's new. Maybe not. So indeterminate limits. So sometimes we can, if we direct substitute in, we get indeterminate. So our two methods are using some algebra and you have to cancel things out, right? Or L'Hopital's rule. And today is about L'Hopital's rule. Done algebra before, so I'll save that for later. So here's what I mean by this. L'Hopital's rule. You get like 0 over 0 or infinity over infinity. It doesn't matter if it's positive or negative. It's still infinities. Then what we can do is, and it's a fraction, we derive the top and then derive the bottom, and then we try again. So you don't do a quotient rule. You just like derive the top and bottom separately. And then you check again. And then you can keep doing that if it's still indeterminate. So, for example, now in the algebra way, I would take a problem like number 1. I could cancel out the x's, and it was equivalent to 1 over x plus 1. We're plugging in this limit, and you'd get 1 over 1, so just 1. Now, in the L'Hopital's rule way, let's imagine I distributed this out. This would be equivalent to of x over x squared plus 1. Well, you plug in 0, you would get 0 over 0. So we'd have to L'Hopital's rule is divide it by the top and bottom, or derive the top and bottom. Derivative of the top is 1. Derivative of the bottom is 2x. Yep. Wait a minute. Nope. That was supposed to be x. X squared plus x. 2x plus 1. Now you'd plug in that 0. You'd get 1 over 0 plus 1. So it's just 1 over 1, which is 1. So basically, you can derive instead, right? Same thing in 2. I plug in a 2. I would get 2 minus 2, 0 over 2 squared. So 4 minus 4, 0. 0 over 0, L'Hopital's rule. Derive the top, I'd get a 1. Derive the bottom, I'd get a 2x. You check the same limit. You get 1 over 4. Could be the same over here. Now, they don't always come out to numbers. I think all these do, but let's find out. So if I plugged in a 1, I'd get 0 over 0. That's bad. So then I'm going to plug in and derive it. So it's going to be 3x squared over 1. It would just be 3. You plug in the 1. Now, so it's L'Hopital's rule. Folks, there's stuff with infinities, but try it on your own. Khan Academy. The other part of this lesson, they sometimes, this is the tangent line approximation, right? And there's a big wall of text right here. So in many instances, finding a value of a function is difficult or impossible. With the use of calculus techniques, we can approximate the function value by finding a y value in the tangent line of the function. Since the method involves using linear function, we call it the local linearization approximation. Okay, all this lesson is about is like, hey, you can do the tangent line and then plug in values for the tangent line. And to approximate the function, so let's say I had this graph and I had this function. There's my function, and this is the function f, right? And let's say at a certain point on here, let's say on f, at this point here, maybe that's like -3. Oh, we can draw the tangent line to -3, and it looks like this. And then the idea is that I have this a tangent line, I have this equation for the tangent line, and whatever this is, in y equals mx plus b form. Sure. I can use this line maybe at x equals -2.9. Instead of using the actual y value of this graph, I can approximate that y value with this tangent line. You might ask, so what? Why don't you just plug it into this function? Why do you need to approximate? I have one example coming up where I think it ends up being useful. But I don't know. I don't really understand why this is a separate thing. One thing I would like you to know is sometimes you see local linearization approximation. They use those words, and I've seen that on the AP test. It's the same thing as saying find the tangent line. I've seen that in practice. So, like, here's an example where it might be a little more useful. Because sometimes a function's hard to evaluate. So imagine the function f of x equals e to the x. And we have a tangent line at x equals 1. So, like, it's doing that. Well, what is f of 1.01? Okay, that e to the 1.01. And now my question to you is, can you do that without a calculator? No. If I said e to the 1, you could do that. Yeah, it's like 2.7 something, right? I mean, you could. Basically, you could. But especially with these, what we call transcendental, I think it's dental or dential. So transcendental functions, like sine, e, like non-polynomial stuff like this. It's hard when you get x values that aren't like some clean number. It's hard to try to figure those out. So, but what if I want to know what this is or just something that's really close to it? Like I have some kind of like margin of error. And it's okay if I'm not exact. What I can do instead is like, imagine I draw the equation for this tangent line, which is in y equals mx plus b form. And that's pretty easy to just plug in 1.01. Like you could do that on pen and paper. You can't plug in 1.01 to e to the 1.01 and do that on paper. And so this ends up, and you might be like, well, you have a computer anyway. Why would I need to do this? We get into this like BC in Calculus BC more when we do like Taylor series. And the idea is that like a computer can calculate this way faster than it can calculate this. And imagine if you had to do this calculation millions or billions of times. Sometimes it's easier just to do it this way. I know it's so funny. I don't know if Zoe knows she's unmuted. Probably doesn't. Okay. So anyways, here's how it works. Oh, wait. I guess I thought it was in that example. So how would I do this? What I want to do is create the tangent line for e to the x. So f prime at 1. So f prime of x would be e to the x. So we say f prime of 1, just be e to the 1. So it's like 2.713. We'll round it. And then we know at x equals 1, the y value is going to equal e to the 1 or just e. So I can create my equation as y minus e equals e times x minus 1. So making that a y equals ms plus b equation, I get e to the x minus e. Okay, distribute this out. And then I'm going to add e to both sides, so I get y equals e to the x is the equation of my tangent line. Now it's a lot easier to say y equals e times 1.01. Okay. E is probably not the best example for this sometimes, but it would be easier to handle. All right, let's do another example. I don't really know what the Khan Academy does. What if you have like implicit equations like this? And like we want to find, something close to implicit functions, something close to the circle. So you have the point 2, -2. It's a point on this graph right here. This graph makes a circle. Use the equation of tangent line to approximate the y coordinate when x is 2.1. So maybe we want to be like, hey, at 2.1, which is like a little bit higher, it's such a small distance, maybe we want to approximate it. All right. So what do I got to do? I have to find dy dx first, y prime, which is my slope. So I'm going to differentiate this. So I get 2x plus 2y, y prime, plus 2 times y prime equals 0. I'm going to subtract that 2x on both sides. Cancel out. 2y y prime plus 2y prime, -2x. Factor out the y prime, both sides. Get my y prime, 2y plus 2, -2x. I guess it's nicer if I would have plugged in numbers. I usually like doing that, huh? My y prime would be -2x over 2x plus 2. I'm going to plug in 2. So -2 times 2 is 4 over 4 plus 6. Oh, 4 plus 2. -4, 6. -2/3. That's my slope. So I can write my equation. They're going to move this. I can write my equation as y minus -2, so plus 2, equals -2/3 x minus 2. I think it's easier to isolate the y for this. I'm actually going to move this down. I don't even want to do that second part. Skip that. So distribute that -2/3 x plus 4/3 send this to Narnia. You want to subtract that 2 on both sides. 6/3 is 2. I get my equation that looks like this. Now I can plug it into 2.1. That's annoying. Like, oh, it's this weird fraction, and now you got to use a calculator too. So y equals -2/3. 2.1 minus 2/3. Oh, and it's calculus, so I would never simplify. Or if you need to, plug it into a calculator. That's the idea behind this. You just go for it. Yeah. Uh-huh. Oops. That changes everything, huh? Not everything. Uh-oh. That should have been -4 plus 2. -2. Changes that to +2 for my slope. Yeah. So now that's positive 2. And that becomes 2x minus 4. I subtract 2 on both sides. And now I get 2x minus 6. Oh, that's a lot easier. And then I'm too lazy to do that. So your y could be 2 times 2.1 minus 6. That's way easier to deal with. So 4.2 minus 6, negative 1.8. Yeah, good call. There you go. Oops, my bad. I hope these parts aren't, I don't know. I hate doing these kind of things, but that's what you do. Okay. You find the equation of the tangent line. Last one I want to do, just to show this, a little less work here, but they give you all the information. This is where like, oh, I'm going to use this local linearization to approximate. Whenever you hear approximate, it's tangent. So this is where I go, tangent line. And since this part means that's negative 2, and then I'm at the point xy is 2, 3 because of this information, I can create my tangent line as y minus 3 is negative 2, x minus 2, which is y minus 3 is negative 2x plus 4. Add 3 to both sides. I get that tangent line. And then you can approximate it by plugging in 2.1. So y is negative 2, 2.01, 7, negative 4.02 plus 7, 2.98. Looks right. So sometimes they just give you this, like, this problem looks simpler. They use this word. You're like, what does that mean? There you go. It means tangent line, and then plug in this x value. That's all I got.